In this lesson, we are going to look at a theorem which is known as maximum power transfer theorem. Okay, so let's just say you have a variable resistor that is connected across a given network. Okay, so this is my network, okay, or in other words, this is my network and I have connected a variable load across this network. Okay, we've just seen that this particular network can be transformed into a equivalent Thevenin's network, or it could also be transformed into an equivalent Norton's network, right? So this is the equivalent Thevenin's network and this is the equivalent Norton's network. Over here we have a voltage source VTH connected in series with RTH. Over here we have a current source IN connected in parallel with a resistor Rn, and Rn is same as RTH and IN is same as VTH upon RTH. Okay, so if you want to find out what is the maximum power that can be derived or that can be delivered to this particular load, then you know what is the current that is flowing through this load, right? The current would be given by either this or this. Okay, so over here my current through this particular load is given by I is equal to VTH upon RTH plus RL. Okay, over here my current is given by I is equal to IN into my Rn upon Rn plus RL. Okay, just recollect your RTH is equal to Rn and your IN is equal to VTH upon RTH, which is equal to VTH upon Rn. Okay, so if over here you are going to replace your IN with VTH upon this, what do you get? Your I is equal to IN is VTH upon Rn dot Rn upon Rn, which is RTH plus RL. Okay, so basically what you have is VTH upon RTH plus RL. Okay, so the current is basically same in both the cases because the two circuits are equivalent. This is Thevenin's equivalent circuit of this particular network and this is Norton's equivalent circuit for this particular network. Okay, so we know the current that flows through this RL. Okay, the current is VTH upon RTH plus RL. You know, power that is delivered to a source or to a load is equal to voltage into the current, or for a resistor it is equal to I square R. Okay, in our case the R is RL. Okay, so this is equal to current. What is current? Current is VTH upon RTH plus RL. So it is VTH upon RTH plus RL the whole square into R. What is the R? R is the load resistor over here. Okay, so the power is equal to this. Okay, now you can just simplify this further. This is equal to VTH whole square upon, you have RTH whole square plus RL whole square plus 2RTH into RL, and you have a RL over here in the numerator. Now if I take this RL in the denominator, what I get is VTH whole square upon RTH square upon RL plus RL square upon RL is a single RL plus 2 RTH RL upon RL is 2 RTH. Okay, this is